Thank you all for coming here. I apologize for a delay of this tutorial due to some scheduling issues, so welcome. But I guess the upshot of this is that you'll have special attention. So if you have any questions, just stop me, just feel free to interrupt me, and feel free to ask those anytime you'd like. I believe also this tutorial will be recorded and will be available online after the presentation. So, if you have any other questions, or you can review it, I guess, and then please feel free to email me with additional questions. Okay, so I'm going to be talking about Air-Microfluidics, and this is basically a technology that we're developing in my lab and in a group that we call the Air-Microfluidics group. I'll give you an introduction to what that is. And the beauty of this technique is really applying microfabrication technologies to making sensors really, really small, sensors for air quality. And the whole goal really is to create lab-on-a-chip devices that can analyze ubiquitous air quality. So that's kind of what we try to do with this. And that actually basically is an introduction to this slide here. And so we're using the same tools that are used in regular microfluidics. However, we apply them to handling gases or air, mainly air, but also gases. In this talk, I'll mainly talk about particulate matter sensors. I'll talk a little bit about chemical sensing and some other things, but I'll focus mainly on particulate matter just because for air microfluidics, that's the applications that seem most promising, most exciting, and also most challenging. Okay, and so what we really hope to achieve with kind of air microfluidics is to be able to take really advanced, complex, and expensive instruments and then shrink them down into a size that can be very small, that potentially can carry with us wherever we go, maybe even incorporate into a cell phone, and also reduce the cost dramatically, right? So that's kind of where my group is going with this. So why do we need to have ubiquitous air quality sensing? Well, it turns out that indoor air quality and air quality in general has some severe health effects. Okay, so we have to be very concerned about the air we breathe. Some areas, like I think today maybe it's not too bad, but sometimes here in Delhi we can see poor air quality. It's not all that great, but a lot of population in the world is exposed to poor air quality, and so we would like to know this, right? So there are some really staggering statistics showing how many people are actually exposed to poor ambient air quality, and in fact we all are. Frequently, pretty much on a daily basis, actually, just going from home to work, exposed to poor air quality if we're stuck in traffic and this was actually planned just to make sure that we underline that effect. But anyway, it is actually quite important to know what we're exposed to. What you can't see can actually harm us. So in the U.S., we have the Environmental Protection Agency, and they have actually outlined what they call criteria pollutants, which basically are pollutants in the air that they are concerned about. And there are, of course, a number of gases: carbon dioxide, VOCs, nitrogen dioxide, ozone. But particulate matter is the one that they are very much concerned about, and it's kind of on the top of their list. Also because the instrumentation there, type of sensors, are a little bit lagging. So it's kind of important to know what's in the air. Specifically for particulate matter, there are many sources. Just to kind of give an introduction to what particulate matter is, these are solids, liquids, solids or droplets that are suspended in the air. And there are a number of sources that generate those. Things like diesel exhaust, tobacco smoke, fires, could be water spray, could be just dust that's aerosolized. They flow through the air, and our concern is that some of them are actually very small. And if we're exposed to this dust, this floating dust in the air, what we call PM, then the small ones, small particles, will actually travel down our airways. We're going to inhale them, and they cause a number of really bad things to our body. It turns out that the smaller they are, the worse actually that we are off breathing them. So, coarse particulate matter, which is basically classified by the diameter of the particles, they usually settles in our throat, thorax, and kind of in our mouth and nose. They are maybe not so bad. But the finer particles actually travel further down our airways. They get deposited onto our lungs. They also are deposited into the alveoli in our lungs. And actually, some of them cross the air-blood barrier. Okay, and so and actually starts traveling in our cardiovascular system. So not only do fine particulate matter cause issues with our lungs, so things like asthma, for example. For example, in Chicago, which is the city I'm from, there's a lot of ambient air pollution issues. It's a metropolitan city. There's lots of air pollution. The incidence of asthma are actually several times higher than the national average in the U.S. just because of exposure to different particulates. So it causes problems with pulmonary function, but also it's been shown to cause high blood pressure. It actually has been shown to travel through the blood into our brain, and there are some studies now coming out that there's actually dementia and Alzheimer that has been linked into exposure to particulate matter. So the short story is a lot of the studies actually are coming out now, and they've been coming out in the last 2 years. So we do not fully yet understand the negative impacts of particulate matter. Okay, but it's very serious. And in fact, the Environmental Protection Agency is considering revising their standards for exposure to even lower exposure limits than they have right now. But in general, when we talk about particulate matter, we're going to classify this into coarse particles. Again, those are the larger particles that are maybe not so bad. Usually, they are around 10 micrometers in diameter, maybe a little bit below that. But a fine particulate matter, which in this case is particles that are less aerodynamic diameter, that's less than 2.5 micrometers, those are the fine particles that we should be worried about. So if you hear people talking about PM 2.5, this is basically what that is. And then, of course, as the diameter gets smaller, they get even finer. And so really below 1 micrometer in diameter, we're now start talking about ultrafine particles, okay? And so, for example, ultrafine particles will be found in diesel exhaust. So a lot of traffic pollution has ultrafine particles associated with them. And in fact, it's been recently found that we can actually see particles that are even smaller than this. So here, about 100 nanometers. It turns out that the exhaust from airplanes and airports is actually finer than this and has much smaller mean diameter. And there are studies now coming out showing that the plumes from those travel even further. Okay, so short story is fine particles bad, and we're still trying to fully figure out the health effects associated with them. But we know it's not good. So so there are a number of exposure limits that are provided by various agencies. So, for example, US EPA, the Environmental Protection Agency, states that exposure to fine particulate matter, this is PM 2.5, should not exceed average exposure. This is annual exposure. This is something, let's say, if you work somewhere at your workplace, you're exposed to it day in and day out. So annually, you should not exceed the exposure of 12 micrograms per cubic meter. And so here is a little bit how these limits are set. So this talks basically about mass. Okay, so for PM 2.5, the allowable mass of these particles. So, let's again refresh kind of what PM 2.5 is, right? PM 2.5 is suspended particulates in air of mean diameter 2.5 microns or smaller. Okay, and there's actually a cut point curve, and we'll get to that when when we get there, but let's just think about, mean diameter 2.5 or smaller. The average annual exposure continuously to those particulates cannot exceed 12 micrograms per cubic meter. So, for example, in this room, it's a little bit hard for me to actually say how much it is just because of some of the smoke coming in from the outside. But I know that if this would be, for example, in the US, and we only have 3 people in the audience here, this would actually be very clean. So we would be maybe at 3 micrograms per cubic meter. Okay, if this room would be full, we probably would be approaching 15, maybe 20 micrograms per cubic meter, just to kind of give you an idea. Okay, so it doesn't take a lot to get into this limit, right? And so this is why tracking this is very important. And then they allow actually kind of the peak exposure go up a little bit, right? So this is all kind of mass of a certain particulate size per cubic meter. Okay, and of course, coarse particulate matter, so PM10, that will settle mostly in our throat. The limits for those are much higher. Okay, but you have to realize though that PM10 also includes PM2.5, right? So PM10 actually says particulates of 10 microns in diameter or smaller, right? So PM10 will have PM2.5, but of course the mass distribution of PM10, if we have kind of an average kind of distribution, most of the mass will be in the higher portion, right, of the spectrum. So it's kind of the bigger particles will carry most of the mass. So if it's on average PM10, it's not so bad. But if we're only talking about the smaller particles, then it gets bad really quickly. Okay, and of course the number of particles here would be greater to generate this mass because the particles are smaller. Okay, and we have a similar thing from the World Health Organization. Again, they're actually more stringent than PM10, but you can see that again, PM 2.5 is kind of similar to what US EPA gives, and then PM10 actually is more restricted, but still a little bit more relaxed than PM 2.5, just because those particles are bigger. Okay, so this is a little bit about particulate matter, but as you can see here, for example, this is a picture from I think one of the cook stoves taken in Africa. So it's very prevalent to do indoor cooking in Africa, and so that's, for example, a big problem, right? So we have people that cook indoors. You can see actually this is how they make their food. They're exposed to all the smoke, right? This is, if you're exposed to something like this is not about milligrams per cubic meter. Right? And so it gets really bad really quickly. So you can think about these particles now getting into the lungs, permeating through the cardiovascular system, and causing really very adverse health effects. For example, a study that came out recently showed that if we take just this concentration and we increase the exposure by 12 micrograms per cubic meter. So we double this above the limit. So depending on which one we're looking at, let's say that we talk about this one, and we exercise. Okay, it turns out that additional exposure negates the health effects of exercising. Right. So it doesn't really take much to actually cause us to be unhealthy. Right. So the question is, if I want to go for a jog here today, I would definitely not do it, right? It's just too much particulate matter. So it would be good to have instrumentation that tells us really what's in the air. And particulate matter, by the time you see it, it's kind of too late. We've been exposed to a lot of it. Okay, so when we started looking at this, we said, how can we create some of these instruments we can carry with us? And a lot of the instrumentation right now to measure particulate matter is really expensive. You have detectors that are, tens, if not hundreds, thousands of US dollars. So there's a problem of you can't just go out there and buy a reliable PM 2.5 detector. So maybe we can shrink the cost down. And so we looked at microfluidics, and so it turns out that Air-Microfluidics is just microfluidics. Actually, microfluidics have been around since 1980s and have dramatically reduced the cost of some of the laboratory testing that traditionally would take a long time and be very expensive. So, for example, we can now determine our DNA, right? We can figure out kind of where we're going. At least in the US, there are a number of companies. You take a little bit of saliva, you send it in, they sequence your DNA, and you get answer that you're coming from this part of the world, your ancestry, and so on. That's done through massive immunoassays, okay, done in microfluidics. So actually taking kind of a whole lab, right, reducing it to something that's on a chip. So we have lab on a chip, allows us to dramatically reduce the cost of doing the analysis. And there is some other, of course, examples that are catching on. So ultra low cost microfluidics on paper. That's come out of the Harvard group, and then some other things. But what's happening is, at least with the genomic applications that really caught on, we've shown a dramatic reduction in cost for these type of devices. So Air-Microfluidics, just kind of going back to it, basically tries to achieve the same thing that liquid microfluidics was so successful at for some of these applications, right? To reduce the cost and hopefully create the same type of complex microfluidic lab on a chip devices that traditionally, these instruments cost, again, thousands or maybe $100,000s of dollars, but now we can get them very inexpensively, and then potentially maybe we can make them so small that everybody can have them, and maybe we can actually have them embedded into a cell phone, right? So I would love to have a cell phone and I travel around, like for example today, right, to figure out exactly what am I exposed to. We can actually, there are a number of sites, and so I'll get back to it a little bit later in my talk, but there are a number of sites like US EPA, for example, tracks air pollution in Chicago. I think we have 2 sites. Here in Delhi, I was able to Google the US consulate that actually posts their PM 2.5 readings. The problem, though, is this is one reading, and that can vastly misrepresent what we are actually exposed to. So, for example, right now, I cannot tell you what we are exposed to right now, right? I could guess it if this would be in Chicago. I don't know here, just because I have no way of telling what the filtration system in the or air handling in this hotel is, but the air outside is actually pretty bad. So, and I can smell the smoke if we step outside of this room. So we don't know, right? If we had a little app on our phone, we could easily tell what we're actually exposed to. Okay, so that's kind of the motivation why we need these things. So what's interesting, when we started looking at air microfluidics, it turns out it's actually vastly different from liquid microfluidics. It is still technically microfluidics, because a fluid can be both liquid or gas. It doesn't really matter, it's still a fluid. However, there are some fundamental issues that make it more challenging, but also potentially more rewarding, okay? And so that's kind of what I would like to stress here. So first of all, with any kind of microfluidics, right, you're talking about very small volumes of your fluid confined by microfabricated structures. That's basically what microfluidics is all about. And so because there is this huge ratio between surface to volume, right? Mainly your fluid is exposed to large amount of walls. There are big concerns with wall effect. So, for example, in liquid microfluidics, we always deal with the boundary layer, right? So there's always, let's say, we talk about laminar flow. Let's not go into turbulent flow, but in laminar flow, there's always kind of this boundary layer, the shear flow between liquid that's not moving, fluid that doesn't move very much close to the walls, and to the fluid that moves a little bit faster away from the walls. Okay, so those surface effects actually affect how particles or other suspended things in that fluid will flow. Okay, so those are some of the issues. With air microfluidics, okay, we have basically the same problem. However, it is now, because there is air, there could be things like charging that will then start affecting how these particles also move. So in liquid, you would see the charging is not so much of an effect, because any charge would dissipate quickly through your liquid usually. through some kind of ionic exchange. That's not the case in air microfluidics. So we actually have to create our channels out of conductive material. So this is, for example, a picture of some of the channels for our detectors. These are built in silicon for the reason to basically be able to deal with this discharge. The other big difference is, so you have wall effects, right? The other big difference is that in liquid microfluidics, there is usually a big mismatch between the dielectric constant of whatever suspended in this liquid and the liquid, right? So if we have, for example, let's say particles suspended in water, let's say there are cells, okay, or any kind of other particles. Water is usually very highly conductive, and then depending on the ionic fluid in the cells, or if it's particles, it actually may be a dielectric medium. There is a big difference in the dielectric constant between the two, which means is I can use a principle called dielectrophoresis to actually move these particles around in that liquid, and dielectrophoresis is often used to concentrate particles away from the walls. Okay, and that's done very often to basically push things away, concentrate them into the center of the channel, and avoid fouling of the edges of these channels. And it can be done actually relatively efficiently. The problem is, if we do this in air, the dielectric constant of the air, relatively speaking, usually is around 1, right? I mean, it's air 1. But the particles usually are at the same order, right? You're going to have, of course, droplets going to have a little bit different dielectric constant, but usually we talk about a mixture of solids and droplets, and then solids will actually have a dielectric constant that's closer to 1 as well, maybe 2, maybe 3. And so we cannot really rely on dielectrophoresis to concentrate these particles away from the channels. And it turns out, because of also charging that still happens, even though we try to mitigate it, it's really whatever we do usually causes the particles to propagate towards the walls. So wall losses are a big concern. And I'll show you later in this talk some of the kind of more advanced methods we're using to eliminate wall losses, okay? But that's something that's an issue. Particles also settle much faster. Obviously, they're always propagating at the terminal velocity of the particles, right? So you have to calculate that into your design. So by the time your particle enters your channel till it exits, it needs to remain suspended. Okay, so you have to make sure that you have certain flow velocity through your channels. Again, not so much issue in liquid microfluidics. Similarities, right? Batch fabrication. Again, we use microfabrication techniques to create these channels in the same time in parallel. So it's a huge cost reduction. Of course, power. Again, that's same thing with liquid microfluidics. We push less fluid through these channels. Okay, so power usage much less. And then it finally allows creation of these wearable devices because the whole system is just smaller, right? So that's also something that's similar. So again, differences are the way things move in these channels is a little bit different when we deal with air. Okay, so a little bit more challenging maybe, but some of the same advantages with respect to cost reduction. I have a couple of slides kind of showing the cost. Usually when we talk about microscale things, we can look at a linear dimension, in this case L. So again, the cost will actually be proportional to L cubed, just because we have less material, so we can make things smaller. That's pretty simple. If we look at the power actually scales just with L linearly, which is basically what it means is that we need less power to push the fluid through the channels, but because there's actually more walls, there's more pressure, right? Because we're contacting the walls a lot more, and so there's actually more losses in the system. So it doesn't scale with dimension cubed. It's just a linear savings. Okay, but still it requires less power, which is great. Okay, and then we talked about the wall effects, right? So of course we're going to have the smaller we make things, the more of these wall effects we will see. Yeah, I already mentioned this with the dielectrophoresis, which is often used to move move things in liquid channels. Again, in microfluidics doesn't work so much. So really, whatever we tend to do, in general, the particles spread out. So that's something that we have to design our system to basically be able to account for. And I'll show you some ways we deal with this in our devices. And again, the number one thing is to make sure that we conduct any kind of charge buildup away from these structures. But there's another thing that we found, which is quite challenging when we started working on this, is what we call the characterization challenge. So it turns out that air microfluidics is really a novel field. There are just a few groups that are working right now at making these kind of complex devices based on microfabrication. So because we operate with such a low volumes of our fluid, we're always kind of operating in this low flow regime, where the flows we deal with are, let's say, all our devices, in fact, are below 50 milliliters per minute. And usually the interesting devices, or the flow we would like to measure, or things that happen at that scale, are from about 5 milliliters per minute to 0.1 milliliters per minute. Okay, so very low flow. The problem, though, is that if we look at the air quality equipment that technically or normally is used there to characterize how these instruments work, we look at much larger flows. Okay, and so the problem is now if we actually connect our device into some of these devices, like a nebulizer that generates particles, condensation particle counter, right, that can be used to actually detect kind of what flows through our device and if we have any losses, or a QCM, the signal from our devices sometimes will not even register. Okay, so there's a lot less of the flow that we have. So that's one of the challenges we had early on. This is actually one of our early particulate generating systems. You can actually see we have a microfluidic channel system here. This actually was when we were evaluating one of our microfabricated virtual impactors, which I'll explain to you how they work a little bit further down in the talk. But we had to connect these very low flows into the entire system. We had a particle generating system here. We have condensation particle counters here. We had a QCM attached to it right here, and it was very difficult for us to actually see anything. So because of this, we actually had to develop a lot of the measurement techniques from scratch. I'll show one of them to you, which we call optogravimetric technique. And then I'll mention one that we are currently perfecting, which actually is called flow strobing particle velocimetry. Okay, but so there's basically devices are smaller, but to characterize them, it actually takes a lot more work than normally. And again, because liquid microfluidics is more developed and has been around for much longer, these instruments already exist, right? Pumps that pump, pico or nanoliter volumes and measure them very precisely. They are already out there. In this case, we actually have to build these things ourselves. Okay, but of course the rewards are huge, right? So if we are able to solve all these challenges, then we can now start talking about miniaturizing these instruments, right? Putting them into a number of portable devices that we can all wear, potentially put into or connect to our cell phone, right? And so just talking to particulate matter, we could potentially look at the size distributions of the PM suspended in the air. Maybe we can do chemical analysis. So we have some projects in my group that actually look at chemical speciation of PM. And then I also have one student, and actually I'm expanding this effort, looking at bioaerosols, right? So maybe we would like to see what's suspended in the air. Maybe it's not just the mass, right? But maybe we look for active particles, viruses, bacteria, right? I definitely would like to be able to, screen and see if the flu vaccine that I took, a month ago, if I walk into an elevator, right, and somebody's coughing, whether they have the flu strain that I'm vaccinated against, or maybe I should take the next elevator. And then, ultimately, if we can all have these devices on us, we can talk about condensing them into the cloud. So there have been some efforts recently looking at PM sensors attached to Google streetcars in San Francisco that actually measure and create the pollution map of the Bay Area, right? So, but you can imagine that we can have the same thing, right? If we're all kind of equipped with these sensors, we can then put the data onto the cloud and actually have a map that not only provides, like right now, maybe traffic information, right? Let's say Google Maps, right? But maybe pollution information, right? And so you can actually start talking about some very interesting applications. If you go jogging, right? Can I have an app that plots my path when I go jogging, minimize my pollution exposure, right? Not necessarily the fastest route to get there, but the most healthier way to get there, right? So those are kind of the things that would be interesting. In Chicago, there's a number of sources. We actually had a coal-burning power plant close to where I live that was shut down just about 5 years before I moved there. But there are still some pollution sources out there, specifically in kind of the less affluent neighborhoods, right? And so if there would be a number of sensors out there, and somebody can buy a reliable PM sensor and start making their own measurements, then they can actually potentially use that data to basically say, oh, hey, maybe this is not this plant is not operating according to specs, should do something. So lots of benefits. From my point of view, I'm actually a kind of a microfabrication guy. I started this from the other end. I like to build really small things. My PhD is really on micro-robotics, so building really small robotic devices. So this Air-Microfluidics was new to me. So what excited me beyond kind of the applications we talked about in the previous slide is that the current applications, and this is our 2013 device. Since then, we made some improvements, but the size of it is still pretty big, or it's still roughly the same. But from a microfabrication point of view, there is a lot of room to put in a whole bunch of sensors in there, right? So we're really just starting to scratch the surface. And from a MEMS point of view, microelectromechanical systems, this is actually quite a large device, right? So even though if I show this to an air quality person, they would say, oh, this is, if we had this, it would be great. But it turns out this is actually very small, a very large device from the microfabrication point of view. So there is plenty of room to put all kinds of sensors to basically analyze the air we breathe in, okay? So I think in the future, and there are some groups that are actually starting to work on this also. And we've seen kind of a increased effort, specifically now with kind of increased focus on air quality pollution. So I think we will see some very exciting applications coming on in the near future. From our point of view, where we're headed is basically to create chip level type devices. So this is, for example, one of the concept designs for our PM sensor down the line, something that's about the size of a MEMS microphone. So we have a couple of those in our cell phones already, right? So this could be another chip that we can place into our cell phone. And so something like this, can have potentially multiple channels, can measure potentially multiple sizes of particulate matter, coarse, fine, ultra-fine, maybe even bin it into different channels of these ultra-fine or the particles. Integrate electronics, pumps, and then in addition, we can maybe add some of these other things like gas sensing or bioaerosol detection, right? And so we can integrate all that into a small package, and in some of these applications, right, then potentially we can really have this sophisticated lab on a chip, right, that analyzes the air we breathe and gives you a breakdown of how healthy or how much exposure you're receiving to certain things, and allows you to potentially modify your behavior or alert somebody to what's going on. The application where for example, I really felt like I needed something like this was I was at a conference, I believe in Busan, Korea, and I was put at a conference hotel, which was very new. It was a great hotel. However, there was a strange smell in my room, and after a half an hour, my head was hurting. right? It was not a very strong smell, but I could not have a headache. My suspicion was that there was outgassing of VOCs. I would suspect it was toluene coming off from the carpet. There was new carpet that laid down, maybe some glue that was degassing. I asked to be moved to another room, and the headache went away. But it would be great to be able to pull out your cell phone and kind of take a measurement and say, oh, this is really what's going on. Maybe this is not so bad, or maybe this is just my migraine because of jet lag. So that's kind of our goal. So what I will do in this tutorial is give you an overview over some of the technologies we develop in our lab, kind of where we're going with this, highlighting some of the technical challenges and some of the solutions that are can potentially use to develop these type of devices, and then also go a little bit more over kind of the market case for why this is important. I think we kind of all understand why that is, but let's look at it from some of the market applications. And then finally, towards the end, I'll talk a little bit about our chemical sensor effort, because obviously that's also part of Air-Microfluidics, building these complex devices. And then at the end, I actually will show some additional applications of Air-Microfluidics to a new thing that we deal with, which is called actually remote controlled smoke. It's actually flying micro robots in air, okay? But I usually save that for the last part to kind of wake everybody up, because I'll be talking for 1.5 hours. But that's kind of the other applications for Air-Microfluidics that people may not realize. Okay. Any questions at this point? Okay. All right. So I'll just continue. So I talked about my group. So a lot of the work that you'll see today is done by researchers in our research consortium, which we call the Air-Microfluidics group. And so this was a consortium that was actually founded when I was still a postdoc at UC Berkeley. It is led out of University of Illinois at Chicago, where I'm currently. But it actually builds on collaboration between UIC and UC Berkeley, as well as Argonne National Lab. Okay, and we're currently expanding the consortium. University of Washington is going to join us very shortly, and there are some other collaborators from Army Research Lab and some of the other local laboratories that will also join. If you're interested to see more information about our projects, I encourage you to go to our webpage. You can actually use this this URL code to get there. We also have our semi-annual workshops. We just had one in end of October. We're going to have another one in March. Okay, and that basically showcases of the work that our researchers are doing on various Air-Microfluidic applications. And also usually we have keynote speakers. A lot of times we bring in outside speakers. In the spring we had several speakers from EPA, and then array of things from Chicago. So if you're interested to attending some of these workshops, you're very welcome to visit us in Chicago, but we also live stream these workshops so you can actually see the presentations remotely. So just send me an email, and there should be more information about all of this on the webpage. Okay. What's interesting about having all these multiple campuses is that we can actually use facilities at these different campuses to do characterization and microfabrication. We use both facilities at UC Berkeley and UIC to do microfabrication. We also use Center for Nanoscale Materials at Argonne National Lab to do fabrication. And our group, has a number of projects that are funded by several of the federal agencies in the United States, as well as we're also seeking a commercial partner. So we have several partnerships that are commercializing at different stages of commercialization of our technology. So again, if you're interested to partner with us, please send me an email and we can set something up. I talked about kind of expanding our collaboration. So this is kind of a list of our collaborators that we're also doing joint research with. I just wanted to put this picture here. This is some of our tool sets that we have access to through these consortium. This is actually a cyclotron. This is Argonne National Laboratory, and I like to say this is the largest tool that I ever used to measure the smallest thing. So this is basically a 1.3 kilometers in diameter particular accelerator. And Center for Nanoscale Materials actually is right here. And so what happens is there's basically a set of very strong magnets that contain a beam of electrons that travel near relativistic velocity, so close to the speed of light. And along these lines, they have what they call undulators. So basically, the beam is shaken around a little bit and generates very tight, very precise, but high energy beam of photons. Okay, and so these laboratories all around the perimeter here siphon some of that energy for their unique experiments. What Center of Nanoscale Materials does with this is they actually, and I believe the beam travels this way. They use an undulator about right here to siphon a very high energy X-rays, and they use that for X-ray microscopy. So they actually have the highest, what they claim to be the highest resolution X-ray microscope in the world. They're able to focus their dot into 2 nanometer resolution, and they can actually in real time watch chemical reactions happen in 3D, in a 3D volume. So we've actually used that to prove some of the chemical reactions that happen on the surface of pre-treated carbon nanotubes for some of our chemical sensing. Okay, so basically our collaboration with Argonne here enables us to use some of these tools, which is quite amazing, and you'll see some of the results further down the line. The other thing that we have acquired, and this actually got acquired when I joined UIC, was some of you might have heard about this tool. It's called a Photonic Professional GT tool by NanoScribe. It's actually the highest resolution 3D printer available. So you can see here some of the models that were printed by this tool. And these are some of the scale bars. The voxel dimension for this tool is 100 by 100 nanometers. Okay, that's kind of the lowest dimension. So this actually allows us to print some of the structures in our microfluidic channels that otherwise we would not be able to do. We have not fully utilized this tool yet. We only use it for the remote controlled smoke projects right now. So I'll show you some of the structures that have been printed using that. But we're kind of moving towards this. And so what we're hoping this will allow us to do is to get away from kind of planar edge down geometry for this microfluidic circuits to something that's much more complex and much more efficient. Okay, so, and we're also looking at using it for some of our photonic crystal sensing applications. And then also we are part of or affiliated with the center, Chicago Center for Health and Environment. And so what's very interesting there is this is actually a center that's funded by the National Institute of Health from the United States. It encompasses University of Chicago, so I guess we're actually collaborating with the University of Chicago as well. But like I mentioned before, Chicago is a metropolitan area that does struggle with air pollution. And so through the center, we actually are able to interact with the communities. And so they're really waiting for some of these sensors to come out so they can start making measurements. EPA is also involved with this, so this is very exciting for us. So, together, kind of this whole consortium, the AMFG consortium, allows us to tackle some of these problems in a very exciting kind of joint way. Okay. I talked a little bit again before about trying to build a case for why this is important. I really see three things that are coming together, why this air pollution sensors and this air microfluidic sensors will become very important. One thing is the re-emergence of Internet of Things, right? So when I started my engineering career, everybody was talking about Internet of Things, and things got actually quite chaotic, right? So all these standards were cross-interlinked. It seems now like the Internet of Things is really coming back. We're all starting to talk about maybe a more standardized security and communication protocols between these distributed devices, cloud computing, crowdsourcing of data, all that is coming back. And so I think, like we talked about before, all these sensors coming online will actually allow us some very exciting, very interesting applications. And there are several companies now that are actually coming out with analyzing the data and maybe partnering with Google or Google Earth to do some of this. In fact, I have a student in my lab that's currently looking at placing some of our sensor data using Google Earth Engine. And so Google Earth have actually opened their whole engine platform for scientists to be allowed to put the data on Google Earth and process it. And they also have a massive data set of both satellite images and weather data that we can now start to sourcing and data mining. And so the exciting thing there is, for example, we can look at a point solution for example, particulate matter. I can then combine it with the geographic information, for example, models of buildings in Chicago, and I can look at the wind data, and I can calculate where the plume will go, okay? Those are some of the interesting things that we can do, right? And then you can do back calculation and say, okay, I'm measuring particulate matter here, right? What is the source, for example? So some very interesting applications that are coming on. The other thing is, everybody's really talking about smart cities these days. There's pretty much a smart city initiative in every city. This is just example of Chicago and Busan. We actually have 3 smart city initiatives in Chicago right now, and they're not necessarily talking to each other, which is kind of interesting. But it's quite interesting. And there are also smart city initiatives in New Delhi, in Delhi area as well, and all of them are actually addressing air pollution. So people definitely, this is definitely becoming a concern. Air quality. We're more aware of it. US EPA, for example, has this webpage called the Air Sensors Toolbox, which provides some very interesting resources for sensor developers. It provides benchmarks. There was a report that just came out yesterday that provides benchmarks for sensor developers for testing and kind of quality assurance for sensors. And I must say, EPA is always kind of worried about what to do with all these sensors popping up there. So there's just kind of their way of trying to maybe not really mandate, but kind of apply some quality control to it. So I think, in short, there's a very exciting time for sensor developers, and Air-Microfluidics, I think we see as a way of creating kind of this more reliable air quality sensors out there. In fact, I had a student that works part-time at our Office of Technology Management. A lot of things that we've actually have been developing. We're in the process of either acquiring IP or converting some of our IP. So they're always looking for kind of cases how the market would grow. So again, there's some recent results that kind of showed how bad air pollution, specifically particulate matter, actually is. I talked about the link to Alzheimer's disease, right? So this is actually the reference, 2015, that shows some preliminary data on that, and since then we've actually seen some other references, and then kind of looking at the network of sensors. There are many measurement stations out there. Like this is a map of, for example, over US. You can Google these stations. But again, the cost of these PM monitor stations right now about $40,000 each. Okay, so it's quite an expensive piece of instrumentation, and that's why these dots, even though if you zoom out and look at the U.S., it looks very densely populated. It's really not, right? Chicago has 2 stations, and so really, it's even though you see this the PM exposure data, it will widely vary for actually what you are exposed to, right, based on kind of your location. Okay, so this is just kind of looking at the projection of the market growth. I'm maybe just going to skip this a little bit, but but definitely, our analysis just based on kind of the market growth, definitely the largest market growth that we see are for indoor monitors, indoor air quality monitors. And so we're actually partnering with some companies that are developing air purifiers for indoor, right? So you can actually measure, when your air purifier should be turned on, and then you kind of can judge, ventilation issues, if there's a lot of particulate matter outdoors, maybe you need to recycle air more, those kind of things. I think what we are underestimating right now is the wearable market. It's a little bit difficult to predict because technology is kind of so early on. However, my personal thing is I think this is way underestimated. I think we're at 2%. I think the wearables actually going to be that's going to drive this the market further. Just because if you look at the wearables for recreational workout applications, Fitbit and so on, right? They're gaining more and more traction. We all have or a lot of us have workout apps on our cell phones, right? So I think a similar thing will happen once we start measuring air pollution. And so there are a number of these sensor development projects now that are actually working on putting these sensors out there. What's different in the case of our legacy technology using AirMicrofluidics is that the vast majority of the sensors out there are actually optically based. Okay, and so now if you go on Amazon or on your favorite online shopping platform, you can buy these particulate matter sensors, but they're all really optically based. And in reality, it's basically a optical source that uses scattering to look at particle sizes and size distributions, and then also counts individual particles going through essentially an orifice. The problem there is if you use the optical methods, you have to then back calculate the mass. So if you remember, if you looked at the standards by EPA, WHO, for example, they all talk about mass in a volume of air. Okay, if I'm counting particles optically, I have to do the inversion, right? I will have a signal. I've seen a particle. I kind of know what size it is, although that's not even that precise because there will be big variations based on humidity and based on albedo of that particle. And now I have to assume the density and do it back inversion, okay, to get to the mass, right? So I will get maybe the number of particles, but I don't know necessarily the density of the particles. And so I have to make some assumptions to get to the mass. And then I see whether my mass corresponds to my standard. Okay, the technology that we are working on is we actually use direct mass reading technology using resonators to basically get that mass directly, so weigh the pollution. Okay, and that's actually how traditionally these standards were developed, right? So why are we talking about 10 or 12 micrograms per cubic meter? Well, the way this standard is developed was we had an air sampler, right? EPA still has these air samplers where they pull air through filters, and they pull for a certain amount of time, and then they will weigh the filters, okay? And in front of that filter, there is a fractionator, and I'll talk about this in a little bit, how this fractionator works, that basically excludes the large particles and only accepts particles of 2.5 microns and smaller, so that's PM 2.5. And then they have the filter that maybe over a period of a day gets accumulated with the particles, 2.5 microns and smaller. They will weigh that filter, and that gives them the mass that was added to that filter, right? And so now, you divide that based on number of hours, and you get basically the average concentration in the air over that period of time. Okay, and that's how the standard was developed. So kind of all these optical approaches that will give you the particle number, but they will not give you necessarily the mass. Now, there's of course a debate. What is it really? Is it the number of particles that are harmful or the mass? And so there is case actually being made for ultrafine particles. It's really, there's not so much mass, there's number that really is kind of prevalent. The debate is still ongoing. I believe EU is actually switching to numbers of particles per cubic meter for their ultrafine standards. Okay, but US is holding firm at mass, and there is kind of a correlation there. But again, it's unclear where it will end up. However, for fine particulate matter like PM2.5, we do not expect a change to particle number. Okay, so it's kind of just keep that in mind. So with that respect, these optical particle counters always will have a bias, and they're actually dramatically. I mean, the error is actually huge. So you'll see some of the experiments that we did later on. We actually used high-end optical particle detectors with very well-controlled temperature controlled lasers. They're very expensive, and I'm not gonna say which company we use them for, but we can all buy them, and they're multi-$1,000 instruments. And these instruments were off, but at least a factor of 2 with a lot of the PM that we measure. Okay, they would either over measure or under measure the exposure that was in our chamber. Okay, compared, for example, to diesel exhaust. So there are some issues, and of course there is some, like the ultrafine particles, these optical particle counters will actually not even see. So I'm just going to skip actually this. This kind of just talks about our technology and why this is different, but I'll talk about these components in detail when we actually look at the devices. These are some of the sensors that have been developed or are in development in our lab for particulate matter. So you maybe have read some of our papers, but I'll talk about this a little bit more in detail. But again, we're not working on optical particle counters. We're mainly using, like I said, the principles of Air-Microfluidics to separate and guide particles and then deposit them onto mass sensing resonator to actually weigh them directly. Okay, just looking at some, just basically again kind of what I said before. If we use the direct derivametric method, we can actually get at the mass directly. Okay, and then if you look at the distributions, this was actually borrowed from this report here that came out in 2015. But you look at kind of the modality of what's going to be out there when we measure ambient particulate matter. There's usually kind of these two peaks with respect to mass. This is what we're concerned about. There's one, this is where we get coarse PM. This is PM 2.5, right? And then we start kind of go below 1 micrometer. So this is where kind of ultrafines are actually, that's how you define ultrafines, but this is where fine ultrafine particles begin. So you can see that the problem is, about here, so at 300 nanometers, if we have an optical particle counter, the optical particle counter starts not seeing the particles because they're at the diffraction limit of the laser. And you can actually, of course, use things like UV lasers and things like that, right? But you can already see that, even with UV laser, we're gonna see some effects here. So your signal to noise ratio drops dramatically. Okay, your uncertainty goes up, but we're still at this major mode here. Once you get to 100 nanometers, you basically do not see them. You have to use things like condensation growth to actually be able to see these particles optically. Okay, and so again, that potentially adds error as well and makes the whole instrument being much more expensive. But there's a significant amount of mass here, and from health perspective, ultrafine particles they're really bad, right? They're the ones that are going to go into our bloodstream. So, optical technologies really are limited with respect to kind of their applications to specifically these really bad particles. And of course, you go further down, the number of particles actually dramatically increases when we go below ultrafines, but the mass is much lower. And so there's still debate on, what the health effects ratio here is. I think one of the issues is that we are not really, it's difficult to have instruments that measure this mode precisely. However, in this case, we get to a point where actually our immune system is much better equipped to handle these smaller particles. So this is really the range of particles that we can handle very well, actually, from here to here. But really from here to here is the particles that get deposited. Okay. So again, direct mass is great because you can capture this entire distribution. Optical particle sensors, again, they're good at capturing kind of particles on this end, but they will grossly underestimate the particles here. Okay. We looked at secondary market. So we believe that automobile exhaust sensors is also a very potent market for these particulate matter detectors. And so if you look at the modalities of particles from diesel exhaust and gasoline, you can see that they're all in the ultrafine range. Okay, and so that's a big concern. And again, it's even worse for exhaust from jet engines, okay, near airports. Okay, so these are all very bad particles, and you really need these novel methods to be able to see them. And so that's kind of what our Air-Microfluidic direct mass sensors or direct mass sensors are actually very applicable to. And so this just looks at some of the reduction standards. We have India here, so you can see that all these standards actually are looking at not only reduces in gases, but they're starting to look at reduction of emission of PM. Okay, so this is where I think some of these PM sensors can really benefit to detect. So again, I'm just gonna go quickly through this, showing what we can actually address. One of the concerns that, for example, with respect to diesel particles and diesel emissions, is that a lot of equipment out there now is mandated to have diesel filters. We work on some projects for developing sensors for particulate matter in, for example, underground mines. And there is some equipment in these mines that are actually diesel driven, but they have filters on them and catalytic converters, to remove some of the gases, but also remove particles. Problem is, if these filters get clogged, they actually stop working very well, and you will see a increase in the particles that come out. And also, actually, it is a lot of times unclear how well they filter particles below 100 nanometers. So having technologies to actually quickly assess those factors could be very important. So this is kind of just a summary of the market. Again, we envision that the market is growing rapidly for these kind of sensors. But again, it's important to have some quality control and to be able to have sensors that actually see some of these different modes of particles. Okay. Any questions? All right, so let me talk about the technology actually that we're looking at it. So, so this is really kind of application of Air-Microfluidics to PM sensing. So this is I believe, second generation of our Air-Microfluidics direct mass PM sensing device. And so this is, in reality, this device works very similarly to something called tapered element oscillating microbalance. It's a unit that's about the size of a small refrigerator, costs $50,000, and is actually used as a federal reference method by the US EPA. Okay, so what we did here is create a microfluidic circuit using essentially 3 wafers bonded together to be able to measure how these particles work. So this is actually a portable direct mass PM 2.5 sensor. The way this circuit works actually requires a pump, so I haven't shown kind of how we apply the pump here, but it has 2 main components. So there's an inlet and an outlet here. We pull air through the circuit, and we have a initial fractionator that actually fractionates the particulate matter into or extracts the fraction or the size distribution that we want to look for. Okay, it's called a virtual impactor. And then we have a sensor site here, which consists of a thermophoretic precipitator that takes these particles that we're interested in out of the airstream and deposits them on a mass sensing resonator. Okay, and that's how we actually weigh the pollution. And I'll go over kind of these components in detail. But this is this is how our system looks like, right? So the air comes in, we have this microfabricated fractionator that then extracts the fraction, selects for what kind of size distribution we're looking for, and then we have a thermophilic precipitator that drops it down onto the resonator. The resonator changes its resonance frequency as it's mass loaded, and so if everything is equal, if we have the same thermophilic gradient and the same flow through the device, we will basically see a change in the resonant frequency of this mass sensing resonator, which corresponds to the concentration of the ambient particulate matter, right, that flows through the system. Okay, so this is kind of just going the same. This is actually the device. This is generation 1 of the device, but basically the components are still the same. We just redistribute them and made them a little more efficient. So this was published in 2013, but it contained basically the same kind of components. So the first thing is the fractionator, a virtual impactor. Okay, so what's a virtual impactor? Basically, a virtual impactor is a system where we have airstream coming in through what's called the acceleration jet, okay, and most of the air continues, kind of makes a sharp turn and continues to wherever our detector is. That's called the major flow. So acceleration jet, we have the major flow, and then we have something called the minor flow here, where only about 10% of the air continues. So we have a little bit of a flow here. Most of the flow goes this way, so most of the air makes this turn. And so the whole idea of this thing is that we have particles of different sizes inside this incoming airstream, but the larger particles are actually unable to make this turn because of inertial forces, and they're actually being ejected from this major flow into the minor flow and then continue further to the outlet. Okay, and of course, the sharpness of the turn here is decided by the size or the dimensions of these channels, right? So if we shrink D a little bit, then the turn is much sharper, right? And so that basically means that smaller particles get ejected, okay? And that basically decides on the cut point, what's called the cut point of this this virtual impactor. And the cut point basically says that it's the point at it's the size point, and which diameter of particles, for which diameter of particles 50% of them go this way and 50% go this way. Okay, that's called the cut point of a virtual impactor. And there's a distribution. I'll show you in a little bit how that looks like. This kind of just shows some of the computational fluid dynamics that we are creating when we design these things. Again, this is the inlet, acceleration nozzle. This is the collection probe, major flow, and minor flow. And so it's a little bit important, and I mentioned this to you earlier, now we have to worry about settling of particles. So it's important that we size these jets in such a way that the velocity here is such that particles, even though you have larger particles here, they're actually moving faster and they don't necessarily settle in the channel. So you have to take that into account. You will see some sedimentation, some settling, but you want to kind of minimize that. That's one of the design criteria. Okay, and so if I'm just gonna see if I can, does not work as intended, but I think if I click on this, you see kind of a movie. These are small particles, right? So these are actually particle traces. So for very small particles, if this was designed for PM 2.5, you see a majority of particles go this way, and again, 10% of them will follow the flow streams going here, right? So that basically means the particles are not really preferentially ejected out of the flow. However, for larger particles, you will see that now the inertial forces dominate and only very few particles will follow the major flow, right? So if I have my detector here, okay, I will now only see the particles below the cut point of this virtual impactor. Make sense? Okay. All right. So this is how a curve for a virtual impactor collection curve will look like. Okay. So this is again just computationally derived at this point, and so we would have a for example, for PM 2.5, we would strive for a cut point around 50%, right? So I said 50% goes one way, 50% goes the other way. For a virtual impactor, it actually is 45% because we can only get out to 90% collection efficiency here. 10% of small particles will still always flow through the flow that goes through the minor flow. But this is kind of what it looks like. Ideally, we would like to have kind of a steep, curve like this. We get all particles below the cut point and then non-particles above the cut point. Unfortunately, that's very difficult, but I will show you some methods that we can use to actually get there. Hopefully, potentially get there. I think I'm going to have to rush a little bit, so we'll see how that goes. But this is basically what's called the collection efficiency of a virtual impactor, or a fractionator, okay, which basically extracts a certain fraction of particles from the air. All right. Then the next thing is, so now we selected for what size particles we want to do. Then the airflow continues. So in this case, this is the fractionator. The airflow continues to the detection site. This is a view of the detection site through our top wafer, which actually is made out of quartz. And I mentioned to you we use something called thermophoresis to precipitate the particles from the air onto that mass sensing resonator. Thermophoresis works basically by creating a thermal gradient across the channel. We have a heater that heats the air above our mass sensing resonator to about 100 degrees C, and then that basically causes the air molecules to move faster on one side than on the other side. And it's actually, it's a little bit more complicated than this, but in reality, we can view this as the molecules moving faster on one side than the other of the particles, and they transfer some momentum to the particle and push the particle down onto the mass sensing resonator, okay? And so you basically have this continuous rain of these particles onto the resonator that mass load the resonator, right? And now the mass of the resonator increases, and we see a drift in the resonant frequency. And so you can kind of see here is a picture of one particular type of mass sensing resonators. This is actually called a film bulk acoustic resonator. So there's actually a vibration mode out of plane on the resonator, and this nice clean surface does not stay clean for very long. We will mass load the particles, and then with some attached circuitry, we can see how that resonant frequency drifts. Okay. In this particular device, we use some off-the-shelf small fans to provide the airflow through the device. Okay, so we actually have to actively pump the air through, because in order for us to be able to select for the right fraction, this virtual impactor is designed for a certain air velocity. So we have to actually pull air at a certain velocity to make sure that we get the right mass fraction. Okay, this is just showing how this device is fabricated. Again, it's a microfluidic circuit, but using air. Okay, so we have one channel that's etched. We have top wafer that contains the heater, and then we have the deposition detector here. We had to invent some interesting techniques like printing of a resin to be able to bond these things together. I'm not going to go too much into detail there, but you can kind of see here some heaters. This is the quartz wafer. This is the opening where the detector will be bonded to once we fabricate the system. This is some of the results. These are results from our 2013 paper. These are some of the newer results, and this is actually the results. So this, and this are the actual experimental data that shows the collection efficiency of our device. So, if you look at, for example, here, this was done in a chamber at Lawrence Berkeley National Lab. We had a machine that would smoke a cigarette for us. This is, for example, cigarette smoke. The cigarette is being lit. That's grating here, and then it extinguishes itself when the cigarette is smoking out. And the blue line is, I'm sorry, this should be cigarette smoke. This is mislabeled. The blue line actually indicates the reference detector, and then we actually use HEPA filters to bring the concentration down a little bit later. But the red line shows the drift in the resonant frequency, so the rate of the frequency change, right? So again, at high particulate matter concentrations, you will see the frequency change very quickly of that resonator because of that continuous rain of mass being deposited on top of it. Okay, so that basically is how we would then, we calibrate this, and that will give us the change of the resonant frequency, which will then correspond to the mass concentration in ambient air of PM 2.5. I mentioned to you the characterization challenge before, so we actually have to invent some methods how to characterize these systems. And so, at flow rates, where the flow rate through our device actually in that particular case was 5 milliliters per minute, the flow through the minor channel was 0.5 milliliters per minute, much too smaller flows to register on any of the air quality instruments that were available to us. So we invented this method called optogravimetric method, and actually we use it for all evaluation of all our virtual impactors and all our fractionators. What that basically means is we put filters, small filters, in line with the airflow. We balance the airflow just as it will be balanced in the actual device, and then we optically interrogate the filter under an epifluorescent microscope, and we count the particles. And we can count the particles, and then based on that, we can back calculate the mass. And so this is basically equivalent to what you would do, how you would evaluate, a microscale device when you pull through filters and you weigh the filters, except because we're not weighing the filters, we're counting the particles. Our limit of detection is 3 orders of magnitude higher than it would be with gravimetric methods. So we can just count particles, and often, we have just a few particle counts. It's enough to give us a data point. This is actually how our chamber looks like. And so, we have our microfluidic circuit created like this. We have pumps on the outside pulling air through, and then we're generating mono-sized polystyrene beads, mono-sized particles through a dryer, and then distributing them into the chamber. And then based on, we know what particle size we're generating, we can find out what the counts are. Okay, so for example, this is the collection efficiency data for one of our newer devices. And you can see here, this is our computational model. And then we have the actual data acquired through this optogravimetric method. And in this case, you can see it actually matches quite well. We're a little bit shallow here, and a little bit higher here. So there are some artifacts that we see, partly we believe due to some issues at the inlet. Okay, so we see some particle losses actually at the inlet of our device. Okay, but this is kind of the data we would get when we evaluate our devices using this optogravimetric method. So what I showed you before was kind of version 2. This is version 4. This is the one that we're currently working on. I can't tell you that much more about this because this actually, we were just finishing the commercialization phase of this device with one of our collaborators. But this is kind of the direction we're going into, where we have multiple channels stacked vertically as opposed to horizontally. And that enables us to create a device of much smaller dimensions and actually save cost. Okay, so this kind of just looks. So, the circuit becomes more complex. We now have 5 wafers bonded together as opposed to 3 before. But this is kind of technology. And again, at this point, we have only one cut point. There's really nothing in that prevents us from cutting at multiple size ranges. You can have a cascading virtual impactor, and so you can actually look for different bins, right? You can look for PM5, PM 2.5, PM1, maybe ultra fines, right? So you can kind of have multiple detectors. And again, at that point, it becomes much more complex lab-on-a-chip type of device. Okay, so that's kind of the state of the art of direct mass sensing technologies we are now. We were now at. However, when we look at these devices, there's still always the concern that you will see particles accumulating in these channels. And so eventually you will have some fouling. Okay, so one way to do this is to basically miniaturize this a lot further down, right? Create a device that's so inexpensive that you can have multiple of these. When one of them fouls up, you just switch to another one. Okay, if I take this down, and if you recall in the beginning of my talk, I showed that concept of this little tiny device that's basically kind of building on this technology. In fact, the reason this is so big, so this is about 3 centimeters this way and 1 centimeter this way, just to give you kind of an idea. We got 3 and 1.5 this way. This is this size because we're still assembling this by hand in the lab, and anything smaller will require a much more sophisticated wafer bonding technique than we have available to us. But if you take this further down and you create this 3 by 3 by 1 millimeter type of device, which is basically just removing all the superfluous dimensions out of the system, then you can create a device that's only a few dollars if you fabricate in large volumes. Okay, so then you can make the argument, well, if these things foul up, we can just switch to the next device. Okay, so and certainly that's something that we can make the argument for. However, we have looked at addressing that challenge with something we call in-flow concentrators. So we're very excited about this, because this actually is a way of overcoming that challenge, like I mentioned before. You know, the difference with Air-Microfluidics is no matter what you do to the particles, they will actually spread out. But there is actually a way we can condense these particles into the center. And so I'm going to show you some of the approaches that we're looking at. So this is just a motivation. You know, the concentration would work for optical particle counters as well as for our systems. It's just the device we just looked at. One of the issues that we have without concentration is that if we have a channel and deposit thermophoretically onto our mass sensing resonator, well, actually most of the particulate matter flows outside of our sensing region. Okay, so you know, the device is sensitive because the resonator is such high frequency and low mass that we can sense, you know, just a few particles gives us a signal. But if we could somehow get all this air volume, condense it into one kind of concentrated stream, and then deposit all that onto our resonator, I can tell you right off the bat, we would increase sensitivity by 2 orders of magnitude. Okay, and just to give you a perspective, our best devices right now have a low-end sensitivity of 1 to 2 micrograms per cubic meter. Okay, which is basically kind of what we would need to see if we're below that standard that EPA gives of 10 or 12 micrograms per cubic meter. Okay, but we have to integrate for several minutes, right, in order to get that kind of resolution, and roughly, you know, 6 to 7 minutes integration time. If we would be able to concentrate all the particles in this air volume onto the resonator, we could get the same signal in less than a minute, right? So it's really something that's kind of very important. And then, of course, what happens is if we concentrate, we improve how this virtual impactors look like, so we can also get a steeper curve, which technically that's kind of what we want to do. And then also we reduce the fouling, right, because we move particles away from walls. So we looked at 2 approaches. So one is using something called sheet flow. So basically we can actually use clean air and kind of squeeze our particles inside the channel. It's interesting, but it has some limitations because we have to provide this clean air. But I can show you kind of how we did that. These are just some of the computational results. You know, it is kind of a sophisticated microfabrication process. So we basically have a device where the air comes in, we provide clean air, and then we have these grooves that actually provide some mixing of the air. So the air actually wraps around the clean air wraps around the air with particles, and then moves the particles away from the walls. This looks how it's kind of bonded at the end. Let's see here the device, here are the grooves. And when we evaluate it, we get something like this, which is kind of what we wanted. So you can see a region of high concentration of particles. And if you do a scan this way and this way, you kind of get this type of distribution compared to if we don't add the sheet flow. Okay, so this is kind of one way to push particles away from the walls. The problem is it requires this clean air coming in, and so we have to have all this apparatus to provide the clean air. So that may not necessarily be practical. We also, I should mention, we integrated all that into a larger system to kind of measure how it improves the functionality of the virtual impactor, and this is a computational model, and this is what we actually measured. on the outlet filters. So, this is one way to do this. It's not necessarily a bad way. However, it requires this additional clean air. So, then you have fouling of the filters to clean the air. So it's maybe not all that efficient. One thing that we are now moving towards which actually we're very excited about, is something called Air-Microfluidics. And so this allows us to concentrate particles virtually anywhere in the channel, move them away from the walls without this necessarily having access to clean air. And the way we do this is we use the principle of optical tweezers, where optical tweezers basically use confocal cavity to trap particles inside two cones that have kind of increasing intensity of air, of light. And so what happens if we have this this kind of air profile, and we have a particle coming into this cone, both the radiation pressure and the change of the momentum of photons will actually move these particles inside into this waste region right here. And so there is some impressive work coming out of some labs in the UK actually at this point, trapping single aerosol particles inside here and looking for evolution, right? So you can actually see how these droplets evaporate or change over time. What we've done is we propose to use the same principle to concentrate particles. So we've designed an optical tweezer. However, we're not squeezing in 3 dimensions. We've actually left 1 dimension open. So this is kind of like an optical tweezer, except it's not meant to suspend particles. It's meant to essentially put particles not at a point, but on a line. Okay, that's kind of the difference. So we have a confocal cavity that the idea is to actually pump this in this direction, not constrain it in this X direction, kind of pump it and create this intensity profile all along the channel. Okay, and if we achieve this, then theoretically, at least the particles should be concentrated around this waste point here. Okay, so we did some modeling, then we designed a macro scale system to show this. This is just kind of modeling showing the forces, how they would work. And so when we do the modeling, we should see a uniform distribution coming in, and then they go through this region. In this case, this is a region where we have that confocal cavity, and then they become more concentrated towards the end. And so, this thing actually we modeled this for several particle sizes, and it works better for smaller particles, but you see concentration anyway. Okay, so that at least was kind of a theoretical approach to this. We actually built a macro scale system to measure this. This kind of just shows the laser in our lab and the profile here. We make sure that our confocal cavity had that kind of increasing intensity. So this is the high intensity region and then the small ones. Just how we measured it. And so the way we did these measurements was we basically would inject the particles into a quartz tube. Okay, and the way we aerosolize these particles is we avoid pre-charging, so there's not much charge going on. There should be some dispersion here, but it would actually work in the opposite way. So if we see concentration at the end, it is concentration minus whatever wall effects we would see along this channel. We have this confocal cavity here that is pumped through our laser, and then we use this optogravimetric method with a filter attached at the end, right? But now the filter will not have a uniform distribution, hopefully, because we would see concentration. So that was kind of the idea. This is, again, a macro scale prototype. The next step would be to microfabricate this. But when we actually did the results, this is how it looks like. So if we pass particles through that tube with the laser off, you actually see the kind of a uniform profile across the filter. Of course, there are some artifacts coming in, but mainly the particles behave quite uniformly. If we turn the laser on, you actually see this very concentrated dot in the center. That's where most of the particles are being pushed towards it. And the interesting thing is you actually see a depletion region around here, right? So if you remember, there was a increasing intensity of the laser light, okay? But towards the edges, that gradient is not as strong, right? So we're removing particles from this area very quickly and concentrating them, but these particles kind of remain still there, okay? So, the next stage would be design a circuit that, a microfluidic circuit that eliminates some of these, that basically grabs maybe these particles for further flow, or changes the optical cavity to also grab these particles, because those are the ones that cause fouling in the channel. And so, if we plot this, we actually see kind of dramatic results. So you see here, the blue line is kind of the system with laser off. The red line is the system with laser on, and you see this dip here in concentration from this depletion area. And this was scanned in the X direction. You can see the same thing in the Y direction. So it actually works very well. And then, so this is basically the original concentration results. If we increase the particle size, it still works, right? It's just we don't see as dramatic concentration just because particles now are a little bit harder to move around. And then if we reduce the laser intensity, you see less concentration, but still, it works. You need longer residence time. So we're very excited about this because this actually allows us to put, if you will, a conveyor belt to move particles around in the channels, and take that entire air volume, concentrate the particles, and then drop them onto the resonator. So we're in a way on our way to implement this actually into our microfluidic devices. So hopefully in the next year or so, you'll see some of these systems coming up with particles in line. Okay, I see that I am out of time. So I think what I'm going to do, I'm going to just briefly talk to you very quickly about the gas sensing effort, right? So you can imagine now lab on a chip device. Maybe we want to measure what kind of gases we have. We looked at some carbon nanotube sensors that are functionalized with metal oxides. And if you're interested to hear more about this, send me an email. But basically, we have some very interesting results that allow for kind of room temperature sensing of methane and VOCs at very low concentrations. This could be used, for instance, for leak detection. So this is ongoing collaboration with our national labs, and using speciation, using morphology to actually get that speciation, for example, for toluene, and also UV activation. Some interesting chemistry. And then finally, I mentioned to you kind of remote smoke. I don't have much time to look at this, but this is another application of microfluidics, and this is actually looking at looking at microscale flight. So we're building these microscale devices that can be propelled through air for various sensing and surveillance applications. It's kind of very interesting physics there. And you can kind of see these devices fly based on the heat gradient that are attached to them, and then we're now using lasers to actually fly these things. Which interesting there is we see similar phenomena that's actually around microscale flying insects. So it's kind of another application of microfluidics. Not so much for sensing maybe, but still microfluidics. Just to kind of conclude my tutorial, I hope I've given you an overview over this new technology, which very high potential, called Air-Microfluidics. Again, the whole goal of what we're working on with these systems is to apply the principles kind of building this lab on a chip type of devices to allow very complex air quality sensing for greatly reduced cost. I talked about some of the challenges of these technologies. So again, large surface to volume ratios, which has issues with fouling and potential charging. I showed you a potentially very exciting technology called Air-Microfluidics that may be used to remove some of these issues. And And then, of course, the challenges is, to characterize how our system works, because we work at such a small air volume. So there are several groups coming out with kind of their type of air microfluidic sensors. So I think this is kind of just the beginning of a technological trend, and it's going to be very exciting to see what happens in the next couple of years. Even though it's more challenging to build these air microfluidic devices, there's great payoffs at the end. Again, potential is to create very complex devices that we can all carry, that are all inexpensive, maybe embedded into our cell phones. And so, there are a number of initiatives there, wearable applications, Internet of Things, smart cities, etc., that will really benefit from these type of devices. And I think what's very exciting, and this is kind of the direction my group is moving towards, is because there's really that much space, and these are still quite big devices from microfabrication point of view, we can add many sensors onto this small footprint and potentially have ability to use multiple physical sensing techniques to kind of sense the same thing. So not only, figure out exactly what is in the air from looking at, chemical or bio, but also use some of these sensors potentially maybe for things like self-calibration, right? The calibration of our sensors. And then if you connect it to the cloud, you may actually use data from several sensors to allow for some on-the-fly calibration as well. And I think, again, we'll see some of the novel devices and applications being developed in the near future. There are several groups working on this. And we're very excited about this up-to-air microfluidics, because that will, I think, enable much precise and much more reliable particulate matter sensors in the future. And then finally, I just want to remind you that we have this consortium, which have an upcoming workshop in March. So if you're interested, send us an email. We'll invite you. You can attend this remotely, or you're welcome to come and visit us in Chicago. And also, if you're interested in collaboration, we're actively soliciting collaboration, sponsored research projects. Just send us an email. We also have a large IP portfolio on some of these technologies. So if you're working for a company that's interested in developing these sensors with us, please let us know. And finally, I would like to acknowledge the funding sources that made some of this work possible, and also the students who actually did all the work. So this is my group. For good or for bad, a lot of these students actually are or have graduated. So, but have continuously evolving process, I guess. All right. If you have any further questions beyond, I guess, what we have time to today, please send me an email or visit our lab page. And I hope that kind of showed you an introduction to this new technology. And again, stay tuned, because I think there's a lot of interesting applications coming out using microfluidics for air in the near future. So thank you again for attending, and if you have any questions, please let me know.